Hello friends, good afternoon and welcome to EduSet live lectures. Dear friends, as you know that we have started a series on organic chemistry and today we are conducting yet another lecture in the same series. In today's lecture we will be continuing with the electronic displacements and we will be taking part 2 of the electronic displacements. Also we will be talking about reaction mechanisms as well. To discuss this topic we have with us our subject expert Dr. Pankaj Khanna. Dr. Khanna is Assistant Professor, Department of Chemistry in Acharya Narendra Dev College, University of Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, Sir.
Thank you so much. Hello friends, as we have discussed electronic displacement in the first lecture, so we will be moving on with the same further, and meanwhile we would also be discussing about the reaction mechanisms. So as the second part of electronic displacement, we have talked about, in the first part we have talked about inductive effect and part of the resonance and also the electromeric effect. So I would continue in this session, I would be talking about more of the resonance and the examples of resonance and mesomeric effect, it is also called as, and hyperconjugation as the new concept. So starting with the concept of resonance, we talked about resonance as the possibility of more than one structure of a given molecule termed as resonance. So what are the possible combinations, because we discussed a few of the applications as the acidity of phenol and the case of acidity of carboxylic acid, but it was not dealt in detail. So further moving ahead, you can look at the screen as what are the possible combinations which may arise because of the resonance. So the first one on the screen is 1,3-butadiene. So 1,3-butadiene as you know is a double bond in conjugation with another double bond. So the conjugation may be because of the presence of one double bond is very much required in every case. The second thing which is required in conjugation with that double bond may be a double bond itself, as we have discussed about the planarity and other rules of resonance, and we discussed about 1,3-butadiene in detail. So the second example in this context would be an alpha beta unsaturated carbonyl compound. As you can see on the slide, that I have replaced the double bond in 1,3-butadiene with a double bond of a carbonyl group. So again there is a possibility of conjugation and resonance happening, and we will be discussing how it goes. The other possibilities may be that the double bond is in conjugation with an atom which is having a lone pair. This atom X may be a halogen, maybe chlorine, fluorine, bromine, iodine, or maybe NH2 group or OH group, which is having an atom with a lone pair of electrons, such that the electrons may be transferred to the carbon atom and the resonance may happen. Similarly, this may be a carbocation which is in place of X, I have placed here CH2 plus. So a carbocation in conjugation with the double bond may also give rise to another resonating structure. So this is an allyl carbocation. Also the carbocation, the positive charge may be exchanged with a negative charge and we may get an allyl carbanion. So this is also a possibility which will give a resonating form of the given molecule. Last but not the least, we may have a double bond in conjugation with a free radical. So CH2 radical again may resonate to give another structure of this allyl radical. So out of these structures we can generalize that a double bond when in conjugation with another double bond is a possibility, and this double bond may be a carbon-carbon double bond. As you can see on the slide, there is a possibility of a carbon-carbon double bond or a carbon and any other element double bond, or the conjugation of this double bond may be with a lone pair wala atom or a carbocation or a carbanion, or we can say a negative charge or a free radical. In all these cases we may get more than one structure of the given species. So these are the main possible structures which are possible to give the resonance, and there may be an extension to these structures, like the double bond may be extended to form a benzene ring and so on and so forth. So, these double bonds may be extended to form a double bond or a triple bond or a benzene ring, and thus we may have different combinations of the possible compounds which may, or maybe there may be compounds or intermediates which may give resonance. So, moving on, we further go for the resonance rules. We did a few resonance rules in the earlier lecture, but there were no much examples which we did. So, these are the examples which we may take on, like butadiene we discussed in the earlier lecture, and the structure which may arise out of 1,3-butadiene may be a polar charge structure because of the conjugation, like this double bond is moving towards this single bond and this double bond is moving towards the further carbon to give a negative charge and a positive charge respectively, and we may have more than one structure, thus resonance is there. So, out of these two structures, which one is stable if we are asked, then the structure which is towards more neutral kind of non-polar kind of thing, or we may say that non-charged or uncharged structure is more stable than the charged one. So, this one which is having the double bond as such pi cloud is more stable than the charged structures, the plus and the minus ones. So, the non-polar or bonded structure is more stable. Secondly, why it is stable? Because there are you can see more number of bonds in the number 1 structure and less number of bonds in the charged structure. So, more number of bond structure will be more stable, and out of the two structures, or maybe a possibility of more than two structures, the one which are more stable contributes more to the hybrid, as I have written in the first line, that the structure which is more stable will be contributing more towards the hybrid and it will be nearer to the hybrid itself. So, the main structure will be nearer to the most stable form and it will be the maximum contributing. That means that the energy of the most stable form will be nearer to the canonical hybrid of the molecule. Moving on, we may have the other form of double bond conjugated with another double bond, as I have already discussed the possibilities that the double bond is conjugated as to form alpha beta unsaturated carbonyl compound. So, in this also the resonance is formed like this, but there is other possibility of formation of this type, but the resonance rule says that what is the difference between the two charge structures I have made. In one, the electron movement is as shown in the arrows, and in the second one, this one, the electrons are moving in the opposite direction, but the rule says that the more electronegative atom should have a negative charge. So, out of these two structures, this is the one which prevails and this is not happening at all. So, out of these two structures, this one is more stable because of the fact that more number of bonds are here and it is a neutral structure, and this one is that second one and the only one because the electrons will be acquired by the more electronegative oxygen atom, and oxygen atom cannot accommodate a positive charge giving a negative charge to a less electronegative carbon atom. So, these are the possibilities here. The last but not the least, the another possibilities which was not present in the combinations also is a possibility of a positively charged species having an atom or a group with a lone pair of electrons. This oxygen atom has a lone pair and it can donate these electrons to the positively charged carbocation and form a bond, although it is having a positive charge on oxygen. But as the first rule said that the structure with more number of bonds is more stable, this form is also very much stable because of the fact that the octet of all the atoms in this molecule is complete in this structure, which was not the case with the carbon with a positive charge. So, these are a few rules which we have already done, but the examples were left at that moment and we have discussed now. So, moving further, there are two types of resonance effect, as in the case of inductive effect and in the case of electromeric effect, and we may call them as plus R or minus R. But the name is also a little bit changed here. I have written plus R or plus M effect. What is this M? M is mesomeric effect. So, resonance is sometimes given as called by another name, which is called as mesomeric effect. And what is this mesomeric effect? Mesomeric name was given by Ingold, a scientist who gave the name mesomerism, and resonance name was given by another scientist called as Heisenberg. So, these are the different names of the two same things given in some books. There is mesomerism, the other book says resonance, and so on and so forth. So, what is plus R or plus M effect? When the last case we discussed in the earlier slide was the oxygen lone pair is given to the positive charge. So, this oxygen is acting as a donor of electrons to the positive charge. Hence, the term plus here, and meaning that the OH group is acting as a plus R group, giving the electrons to the conjugation. Into the conjugation, it is providing electrons. We will come to know what is minus R and minus M in a while. Another example of this we have already discussed about phenoxide ion we discussed, and in the phenoxide ion we discussed about the electrons of O minus going into the ring. Hence, this O minus is converted into these type of resonating structures we already did in the last lecture, giving for the acidity of phenols. Why phenols are acidic? Because the phenoxide ion is much more stable than the resonance of the phenol. So, why I am telling you again this in the plus R plus M effect? Because this O minus group is giving you the electrons into the ring. So, you can see the arrows are moving inside the ring and the negative charge is dispersed into the ring. So, if we make a canonical hybrid of this structure, it will be having the negative charge moving all through the ring, and we will be having a minus charge in the ring itself. So, donation of electron into the ring means that the electron density inside the ring is increased by this O minus, and hence this O minus group is called as a plus R or plus resonance effect wala group, or a plus M or plus mesomeric effect group. So, how does it matter to the system? What happens? What are the implications? We have done, you can see on the slide that we have done previously the acidity of phenol, and what are the other applications it may hold good here. As another point may be like electrophilic substitution reaction when happens on phenol or phenoxide ion, like the Riemer-Tiemer reaction happening on phenol makes it a phenoxide ion first, O minus K plus, and then the carbene attacks on the potassium salt of potassium phenoxide, and that carbene attacks on the ortho position of phenol. So, why it is having ortho position, or maybe in other reaction a minor product at para position. Ortho and para direction means that the electrophile we would be doing in another session. What are electrophiles and nucleophiles? Those positively charged species are attacking only at ortho and para positions. Because of this plus R effect of O minus, that minus charge is available only on the ortho and para positions. So, ortho and para positions are more electron dense, and hence a positively charged group attaches itself to the more electron dense positions, and it leaves the meta positions as such, does not react with it, because they are comparatively electron deficient than the ortho and para position. So, the one point was this, and the other point is the phenoxide group also becomes an activating group. What does it mean? In the electrophilic substitution reaction, because I told you that there is a canonical hybrid which is formed, which gives a minus charge in the ring, the minus charge makes this benzene ring richer in electrons than compared to a normal benzene ring. Hence, we say that the rate of reaction is fast than the reaction with a benzene group, because more electrons are visible to the electrophile and it is attracted to a greater extent to the benzene ring, which is activated as a minus charge on benzene ring. So these type of groups are called as activating groups. Moving on, next we move on to another example of plus R and plus M, which is the aniline. So you can see on the slide that I have made the resonating structures of aniline. What I am trying to suggest that again aniline, the NH2 group, because of the lone pair of electrons, is a plus R group and it is generating minus charges on the ortho and para position. So it will again be ortho para directing and activating, and also because of this lone pair going inside the ring and due to the plus R effect, the basicity of aniline is less than what is of alkyl amine RNH2s. It is less basic because basicity is by virtue of the lone pair, and lone pair is attached to a H plus ion. The more the lone pair is available, the more the compound is basic. Because this lone pair is going inside the benzene ring because of the plus R effect of NH2 group, this NH2 group of aniline is less basic than a normal alkyl amine. Similarly to the phenoxide ion or the phenol, it will show orthopara direction in electrophilic substitution and will be an activating group for electrophilic substitution. Further, you can see the order of the plus R effect on the basis of the various groups. So, O minus phenoxide ion we have already discussed is the maximum with plus R or plus M effect. The second one is NH2 group, we have already discussed. Then comes the NHR and substituted amines, alkyl amines, which are lesser in plus R, then phenol, then alkoxide, ether OR group, and then the NHCOR. This NH is N is attached on the benzene ring. So these will be the or any other compound, N is towards the N the molecule is attached, and OCOR group. These are on the basis of plus R group. Last but not the least, the halogens come with fluorine, chlorine, bromine and iodine. Why fluorine is maximum in terms of other halogens? Because the overlap of fluorine lone pair with a carbon pi cloud is better because fluorine is of similar size to the carbon, and as we move from fluorine to chlorine and to bromine and iodine, the size increases, and hence you can see on the slide that the order of plus R effect or plus R group decreases from fluorine to iodine. Moving on, the minus R or minus M effect, quickly we can understand what is minus R minus M. This C double bond O group is withdrawing electrons. We have already done it in the resonance structures possibilities, that this O will capture the pi cloud and these electrons will move here to give this type of reaction, this type of resonating structure. Because this O group is taking away the electron from the system, this C double bond O group is a minus M or minus R group. Similarly, a nitro group on a benzene or any other conjugation with double bond is a minus R or minus M group, because the nitro group is taking away the electrons from the benzene ring. In this case, the double bond electrons it is taking away from the system and creating a positive charge on this position. Further, the positive charge is going across the benzene ring and it is present at ortho and para positions in this case. So what are the implications? You can see on the slide the implications. The electrophilic substitution reaction in this case is meta directed. That means that the ortho and para positions are positively charged now, and the only electron dense positions are these meta positions which are not having the positive charge. Hence, more electron availability is present on these positions and a positively charged electrophile can attack on meta positions. Further, they are called as deactivating groups because of the fact that they are taking away the electrons from the ring towards themselves, and there is a positive charge in the ring, and hence the rate of reaction of electrophile attacking the benzene is decreased when compared to a normal benzene without this nitro group. So they are called as deactivating groups. The order of the minus R effect is given below, which is nitro is the most electron withdrawing kind of group in terms of minus R effect. Sulfonic acid, aldehyde, ketone, you can see on the slide the order is given carboxylic acid, ester when attached to the carbon, and amide. So, this is the order which is in the decreasing ability of minus R or minus M effect. Now, we would be moving from the resonance concept to a certainly different concept which is called as hyperconjugation. It may be a corollary or an extension of the resonance, but the difference here is that in resonance we were doing about, what we were doing about was an overlap of pi cloud with a pi cloud or a lone pair or a carbanion or a carbocation. So, we were only interested in the pi orbitals, the electrons present in the pi cloud. But in hyperconjugation there is something which is happening which is different than resonance. So, let us see what is this. Let me ask you a question, as you can see on the slide, that how did the concept of more substituted alkene being more stable, it is stable not stable, stable established. What is it called? It is called as Zetsov rule or Satysev rule, which way you may call it. More stable the alkene, more it is substituted. So, I have taken an example of propene. So, propene is said to be more substituted because ethene, C double bond C, CH2 double bond CH2, I have placed one alkyl group which is methyl group here. So, I have made propene. Propene is more stable than the corresponding ethene. Why is it so? So, for getting the answer, a concept of hyperconjugation evolved. You should understand one point, that these resonance and hyperconjugation things are only hypothetical things which have been given to prove one of the few things which are present already as experimental values. So, in this case we would be coming to the bond lengths also and the evidences. What happens that this pi cloud, there is no space for conjugation, there is no lone pair, there is no carbocation, there is no minus charge or any other double bond. So, what happens to explain the concept of stability of alkenes, this pi cloud was conjugated to the sigma bond of carbon and hydrogen. So, what I have done is, this is a pi-pi bond, I have not made the sigma bonds here, I have only iterated on the pi cloud here. These are the two p orbitals which are overlapping to give a pi bond, and respective hydrogens and carbon-carbon bonds are existing there. I have not depicted them. This methyl I have depicted as, these are sp3 hybridized, 3 sp3 hybridized carbon orbitals which are attached to s of hydrogens. So, what is happening in hyperconjugation? This structure may be resonance stabilized as giving that this pi cloud is conjugated to this carbon hydrogen sigma bond. So, what is happening here? You can see I have made one orbital structure, that this pi cloud has now shifted its electrons towards this carbon completely, so that it is a negative charge, and the electrons of this sigma cloud are shared with this p orbital as a pi bond in this case, and this hydrogen goes out as a H plus ion. So, what is happening? This H plus is standing as such outside the molecule, and a double bond dish character is formed between these two carbons. Single bond has been converted into C double bond C, and a carbanion type of thing has generated here. This is not exactly what is happening, but this is a hypothetical situation which was given as hyperconjugation by the chemist to explain the fact that more substituted alkenes are more stable. So, we would be going into that quickly. This hydrogen overlap, this sigma pi overlap may happen in the case of propene 3 times, one with this hydrogen, the other with this hydrogen like this, and the third one with this hydrogen like this. So, these 3 separate structures are getting formed besides the normal structure of propene, which give the carbon-carbon single bond which was present here, a partial double bond character which was explained on the basis of bond length, and we would be coming to that. But for the stability of alkenes, we should understand that the substitution as the methyls are put on ethene, there is one methyl we got propene. So, there are 3 resonating hyperconjugative structures. We put another 3, we will get more 3 number of hyperconjugative structure, and tetramethylethene, or we may call it as 2,3-dimethyl butene, will be the most stable among the various alkyl substituted ethenes. So, I have written here, thus as substitution increases, the more methyls, more number of resonating structures, and higher is the stability. This effect was given by Baker and Nathan, and it is also called as Baker-Nathan effect, because they were doing a few things, experimental things they were doing, and they got it, and is also, as you can see on the slide, it is called as no bond resonance, because the resonance is having a proton which is not having a bonding with the mainstream conjugation. So, it is also called as no bond resonance. So, this was according to the book Finar. In Morrison and Boyd, another book which we consult usually for undergraduate level, this type of bonding has been postulated, as the hydrogen is not completely gone, but it is having a formal bond with the first C1 carbon. So, all the hydrogens are getting removed and they are forming the formal bonds. Moving further, what are the evidences besides the ZSAV rule? The evidences are, we find that if we move from ethane to propene, the C double bond C single bond bond length in ethane is 1.54 angstrom, but in propene the C2 C3 single bond is of 1.50 angstrom, which is less because of the partial double bond character we did earlier. So, partial double bond character is coming and the bond is getting shortened a little bit. To explain this, hyperconjugation is a very good reasonable answer. Further applications, the stability of carbocations, we have done that the carbocations are more stable because of more number of alkyl groups. So, more number of alkyl groups will give us more number of more inductive effect, and hence tertiary butyl is more stable. This may also be given on the basis of hyperconjugation. So, this no bond resonance, we can convert this carbocation. I have taken ethyl carbocation, and similar to the alkene, you can see that this hyperconjugative structure is getting formed. Another one will be formed with another hydrogen, and the third one in this case. So, we are having 3 hyperconjugative structures. If I complete for all the different carbocations will be having 3, 6 and 9. Methyl is not having any alkyl group attached, so there is no structure. More the number of hyperconjugative structures, more is the stability of the carbocation. So, tertiary butyl is more stable. Similarly, the free radicals may be explained. Last but not the least, you can see on the slide that we can explain the ortho and para direction of the toluene. This methyl group also can undergo hyperconjugative effect, and by virtue of this there is a negative charge on ortho and para positions, and we can explain ortho para direction of the toluene by only hyperconjugation, because inductive effect will only give ortho, then the rate will increase towards meta and para. But ortho and para products are formed in case of electrophilic substitution reaction of toluene, and hence we find that hyperconjugation is a reasonable answer to that. Thank you so much for your attention. Hello viewers, in this session we would be talking about the reaction mechanisms. So, before going to the reaction mechanisms, we should recapitulate a little bit what we have done till now. we have discussed about all the electronic displacement which are happening in the organic compounds, say inductive effect, electromeric effect, resonance effect and the hyperconjugate effect. So, these are the possible displacements of electrons in the carbonyl in the organic compounds which are carbon compounds which are present. So, by virtue of these effects we would be learning various reasons for various situations which may arise when you are doing any part of organic chemistry. Moving on, we would be talking about reaction mechanisms. What is a reaction mechanism? Reaction mechanism we get out of the reactions which are present in any of the reactions, maybe organic, inorganic or any type of reaction we are doing, and these mechanisms are prepared on certain rules. So, today in this session I would be discussing under the purview of reaction mechanisms the nucleophile and electrophile, what are nucleophiles and electrophiles. Then we would be discussing about curly arrows, and then what are the types of reactions which are possible in organic compounds, the addition reactions, the elimination reactions and the substitution reactions. So, moving towards the first part, what do you understand by the terms nucleophile and electrophiles? So, as we are taught at the basic earlier level of the school level of chemistry, in organic chemistry, we learn that nucleophile means nucleus loving. So, nucleus loving means that the species is attracted towards a nucleus. Similar is the case of electrophile, it is attracted to a electron density or maybe electrons. So, considering one by one, you can see on the slide what is a nucleophile. Nucleophiles are species which are nucleus loving. What are they made up of? They may be having a negative charge on them, or there may be a lone pair present on the species. We may depict, you may see in the books or any other content you are following, as nucleophiles may be depicted as Nu minus. So, minus charge is there, or there may be a lone pair also, but the depiction of nucleophile is given in the books like this. And what are the types of nucleophiles, examples of nucleophiles? As negatively charged I have told, so OH minus, NH2 minus, Cn minus, X minus which is halogen, Cl minus, Br minus, I minus and F minus, they may act as nucleophile depending on their nucleophilicity, and these are negatively charged nucleophiles. As for the neutral nucleophiles or the ones which are having lone pairs, we may have water, ammonia, or maybe in some cases we can say that alcohol with the oxygen, like I replace one H of water with R group and I get alcohol, and this lone pair of oxygen or nitrogen may act as a nucleophile. So, why we are doing nucleophiles and electrophiles, we would be coming to that. Second point is, what are electrophiles? Electrophiles are electron loving species, and electron loving species means that they are themselves more than a little bit, they are electron deficient, and hence they are attracted towards the electron density or the electrons. So, what types you can see, they may be positive or they may be neutral, as in the case of nucleophiles. Nucleophiles were negative because they were attracted towards the positively charged center or the nucleus, and electrons are positive because they are attracted to a negative charge center. So, this is basic Coulomb's law. As the charges increases, the attraction increases. They may also be neutral, as the positively charged center may be electron deficient, but not exactly a positive charge is happening on that. The species is neutral because the electron density or the electron deficiency is present in the species. So, we can see that electrophiles are given as E plus, and the various examples of electrophiles are, the basic example is H plus, a proton. You can see on the slide that NO2 plus, nitronium ion, a halide halonium ion kind of thing, X plus. This is quite unusual of the things because we usually relate halogens with a negative charge, but when we would be talking about reactions of that type, so there may be X plus, Br plus or Cl plus is also present. Another type is alkyl carbocation and acyl carbocation. These two are present when we do Friedel-Crafts alkylation or Friedel-Crafts acylation. So these are the types which were positive electrophiles. The neutral ones may be SO3, the sulfur trioxide or carbon dioxide. As SO3 we do the sulfonation of benzene, we use SO3. Carbon dioxide as the one with like the Riemer-Tiemer type of reactions we do, we can, or the coal based type of reaction we do, we can have carbon dioxide or the electron deficient carbenes. So this is dichlorocarbene which is present, which is not having a positive charge, still it may act as an electrophile because it is electron deficient. Moving on further, before going to the reaction mechanism per se, the type of reactions, we should understand a few rules, like what are the arrows which we have been making in resonance and all, what do they depict? So they are called as curly arrow. So what do they do? They are called as arrows which give the direction or movement of electrons. So when you make an arrow, like we did this conjugation earlier, a carbocation, allyl carbocation having a double bond here and a plus charge here, we made the resonating structure of the same. We move the electrons from this electron rich state to an electron deficient position. So we are moving the electrons from where the electron density is high to electron density is lesser. So this is the type which we do. In this case, what we would do? We would do it opposite manner. In an opposite way, we would put the charge, negative charge is electron dense thing, it will go inside and these electrons will move towards this side. So these are the two things which make the reaction mechanism or organic chemistry reactions very important point, because of the fact that we have to learn how the arrows are moved. Students may move this positive charge, the arrow like this towards moving the positive charge. No, positive charge cannot move. The direction of arrow always shows the flow of electrons from one place to another. So we are moving like this. How about a free radical? In allyl radical, we move the half arrow. You can see on the slide that we are moving half arrow, which depicts, the full arrow depicts a pair of electrons which is moving. You can see on the slide the negative charge moving a full arrow, and in case of the free radical, there is only one electron. So one electron, I have made a half arrow. So half arrow will move to this part and another half arrow will take a C double bond C, only one electron of this C double bond C pi cloud, and move towards this side to make a pi bond here, and we will be moving another bond, another electron to this one to get another allyl radical. So this is all about curly arrow rule. There may be another case of example with lone pair of electrons. Again, they go hand in hand as the carbanion structure. The lone pairs are electrons which are present. So the arrow will show the movement of electron, that is the lone pair. So we find that the difference arises when a positively charged center is there or a free radical kind of thing is there. Otherwise, negatively charged things are quite okay, because they depict the electron movement itself. Moving on to the reaction mechanisms, this what we have already done is again reiterated by what we had earlier done in inductive effect. We talked about homolytic cleavage and heterolytic cleavage. So whenever we are talking about reaction mechanism, we should understand again what is homolytic cleavage. Homolytic cleavage is breaking of bonds, single bond into two equal type of things, which is one electron is shared by taken away by one species. They may be same or they may be different. AB also undergo a free radical kind of thing, A radical and B radical, and on the basis of electron density, AB here, because B is more electronegative, so heterolytic cleavage is happening. This was just to reiterate what is homolytic cleavage and what is heterolytic cleavage, so that the mechanisms under which we are going to do are clear to you in a better manner. coming to the types of reactions, I have divided as the preview I talked about that I would be talking mainly about addition reactions, the substitution reactions and the elimination reactions. So, these are the three things which we would be talking, because basic mechanisms happen in these three categories. There are two other cases which may be present, which are called as rearrangement reactions, in which a proper rearrangement is happening, the things are moving from one place to another and giving you a new molecule, and there may be oxidation reduction reactions. So, those two categories may also be there, but those mechanisms are typical and they are having a different foray, or we may say that they are dealt with in a different manner, because rearrangements are like concerted type of reactions, pericyclic reactions which are happening or may be happening in a special case study we may take them, and oxidation reactions are just like electron transfer mechanisms and they do not have proper organic kind of mechanisms which may be discussed here. So, I have taken addition reactions, substitution and elimination. Starting with addition reactions, you can see that what is happening on the slide, you can see that addition reaction may be given as the reactant is reacting with a molecule which is A and B, two parts, any components, and the reactant is just getting the two things added up onto the into the system itself. So, the reactant is having now A also and B also. So, what is happening in addition reaction, that a plus of something is adding, A is adding, and then another plus of something, B is also adding. So, both of the things and all the things which are present there are adding up to give you the product which is having A also and B also. So, when I teach in the class, I say that it is a plus and plus, both the things are getting added. So, for this purpose, you may come to know in a while that we would require a certain kind of arrangement where a pi bond is present, because a pi bond is cleaved and A is added to one species, may carbon may be the case, and B is added to the other carbon, we say in an alkene. So, both the things are added, A and B form the sigma bonds and the pi bond is gone. So, pi bond is not there anymore and we are having an added or addition product. So, this type of reaction is called as addition reaction. They may be classified as, I have already discussed with you the nucleophiles and electrophiles. The purpose was to describe all the reactions under the category of nucleophilic reactions and electrophilic reactions. There may be more of them and we would be discussing as and when they come. So, first of all, electrophilic addition reaction, you have done that alkenes, say an alkene double bond carbon double bond carbon is getting added with A, as I have already told you, carbon single bond A and carbon sigma bond B. So, both the things are added and hence we are getting an addition product. Why I have written electrophilic? Because of the fact that the mechanism, when you will be doing it in details in the topics, when we would be discussing alkenes in this reaction in this lecture series. So, you would be seeing that HBr is added, when HBr is added to an alkene, say propene I have taken here. So, you would recall the school level alkyl halide and alkene chapter, that HBr is added as first of all H plus to the alkene, H plus is added here, a carbocation is formed and Br minus is added to the secondary carbocation. So, this type of reaction in which more number of hydrogen wala carbon gets the hydrogen and the less number of hydrogen, this is having hydrogen 1 and this is a methyl. So, it gets the bromine, is called as Markovnikov addition. So, Markovnikov addition is happening here, and why this reaction is called as electrophilic? Because H plus is also adding, Br minus is also adding, one is electrophile, the other is nucleophile. But you should understand that when you do the reaction chemistry of this, the complete mechanism of this type of reaction, you would learn that the rate determining step will be having the H plus adding to the alkene. When the rate determining step is having H plus, hence you call it as electrophilic addition reaction. If the rate determining step is having a nucleophile which is getting added, you call it as nucleophilic addition reaction. So in this case, Br minus was getting added in the fast step and H plus, which is an electrophile, was added at the rate determining step, hence it was called as electrophilic addition reaction. What is nucleophilic addition reaction? This is the nucleophilic addition reaction. I have taken cyanide ion as the nucleophile, a negatively charged ion. This C double bond O group is having an electron deficient positively partial positive charge carbon atom. We have done an electromeric effect that when a negatively charged thing comes, this will show this movement. As in the case of alkene also, we have done an electromeric effect, the addition of HBr or acids on alkenes. So what is happening? The Cn minus will add up to this, and H plus, which is remaining of HCN, is added to the O minus which is formed. So again we are having H plus added and Cn minus added, but this is called as nucleophilic addition reaction because the rate determining step here is adding the nucleophile into the system. So this is about the addition reaction which may be nucleophilic or electrophilic. The third type of thing you must have done when you did Markovnikov rule, you have done anti-Markovnikov addition also, and in that case we follow a free radical mechanism. That is the case when HBr is added to an alkene in presence of peroxide. So in that case the thing which we get is exactly opposite to the Markovnikov rule. The bromine was coming here, H was going to more number of hydrogens, but due to the presence of peroxide the type of mechanism changes and we get a free radical addition kind of thing. And free radical addition, when we would be doing again the anti-Markovnikov addition type, we would be discussing that we get a 1 bromopropane, not the 2 bromopropane as in case of Markovnikov addition. So these are the three type of addition reactions: nucleophilic, electrophilic and free radical additions. Moving on to elimination reactions, like we did, the addition reaction was a plus plus. Say a reactant is having A and B species present already. So you can take it as a complete reversal of the addition reaction. In addition reaction we were adding reactant and AB. So this is exactly the opposite, but mind you, this is not the reversible kind of thing I am talking about. I am not talking about the reversibility of addition reaction. I am talking about the opposite reaction. I am having a reactant which is already having A and B, and I am removing both A and B together. So in I am placing a reactant as reactant because there is a loss of A and B. So somebody would say that, oh, reactant A, B was you were writing here and here you are writing again reactant, it is a product, but I am depicting a product minus AB. So this is the reactant kind of thing. I may have placed a product word here without minus AB, but it would not have depicted that it is exactly opposite of addition reactions. Next point is, I have already discussed, told you that it is minus and minus. So as minus and minus we would be deducing, we would be minusing, we would be subtracting A as well as B. So you can see on the slide that this will result in a double bond getting formed. So we were adding AB to a double bond, we got this type of an alkane type of structure, but exactly opposite. What we are doing, we are taking a system like this which may be a alkyl halide, and using the H and Br are not visible on the screen. You may understand the Br is present here, and alcoholic KOH, we are removing H plus and Br minus to get excuse me, to get the alkene, and HBr is going away. So this type of reaction is called as elimination reaction, and you may understand that this type of reaction is may be possible by E1 and E2 type of mechanisms. When we would be doing it in alkenes chapter, we would be discussing what is E1 and E2, elimination unimolecular and elimination bimolecular. So this is all about elimination for now, and we would move to substitution reactions. What are substitution reactions? Till now we have been adding to the reactant or we have been subtracting from the reactant. So addition, complete addition, elimination, complete subtraction. In case of substitution reaction, there is, as you can see on the slide, A is getting replaced by B. So what is happening, that a plus, that is B is coming into the system, and minus A is going out of the system. So the example I take for this type of reaction is of, like in a hockey match or a football match, we have substitutions. What are those substitutions? A player, say maybe Indian player, would leave outside and another Indian player would come inside. So what is happening exactly is happening here. When we would be doing the types of substitution reaction, we would be doing that similar type of thing B is coming into the system and similar type of A is going out of the system. So to make you understand, first of all we will be doing nucleophilic substitution reaction. This reaction is, we would be dealing in details whenever we are doing the reactions in alkyl halides and acyl halides. Alkyl halides, I have taken the example. The type may be SN1 and SN2, as in case of elimination it was E1 and E2. The alkyl halide is getting reacted with this nucleophile, and the nucleophile comes inside and we are giving the Cl minus ion is going away. So what exactly is happening here? The nucleophile is replacing or substituting the Cl minus ion. So you can again confirm from the fact that I talked about a hockey match or a football match, that the same type, when Indian player comes outside, no Australian player goes inside. Indian player comes outside and Indian player goes inside. So similar manner, a negatively charged thing was going inside and a negatively charged species, which is a kind of a weaker nucleophile, is getting replaced by a stronger nucleophile. So this is one type of substitution reaction which is called as nucleophilic substitution reaction. The other type of substitution reaction is electrophilic substitution reaction. It happens in benzene and aromatics. We have been discussing about electrophilic substitution reaction when we were talking about the orthopara direction and all. This is the mechanism of that. I have placed on benzene a group G so that you can identify an orthopara directing group or a meta directing group. So this we are not going to discuss it in detail, but a quick look into the fact that what is electrophilic substitution. This E plus is attracted to the double bond and double bond electrons, and these electrons will move towards the E plus as according to the curly arrow rules, and the H plus of this carbon is going out. So again, when E plus is going into the system, H plus is going out. Because this E plus is an electrophile, hence this reaction is called as electrophilic substitution reaction. The earlier case, nucleophile, because a negatively charged species was entering into the system, it was called as nucleophilic substitution reaction. So you can again notice that as mentioned earlier, G may be orthopara directing or meta directing depending on plus R effect, minus R effect, plus I effect, minus I effect. As in case of halogens, the plus R effect of halogen gives them as orthopara directing, but the minus I effect of halogen make them a deactivating group. So they are orthopara directing but deactivating. So the two things which may be given by G are whether the E will be present at ortho and para or it will be present at the meta position. And the second thing, whether the reaction will go fast, then benzene, simple benzene, then it will be activating, and if it goes slower than the benzene, then it is called as the deactivating group. So these are the substitution reactions which may be placed in case I hope that you have found the discussion done today to the best, and all the best to you, and you can ask for any other questions at the side. Thank you so much.
Dear friends, on that note, we would like to thank Dr. Khanna for coming to our show and delivering this wonderful lecture. Friends, it's our continuous effort to bring knowledgeable and knowledge-enriching lectures to you. On that note, thank you, dear friend, for watching our show. Stay tuned and keep watching. Thank you.